Let's start. Hello, let's start with our today's DSA with this amazing visualizer by dsa.chaicode.com. Use this link to get a 7-day free trial. Okay, let's start with our today's concept first, and it is the concept. It is a very simple concept, and we already use it in this question: maximum depth of a binary tree. Okay, you can go and check out this question. I am just tell the concept to everyone. Okay. The link of the maximum depth will be in description if I remember. So to be very honest, so this is the simple thing. We just go to every node and we just add one values to it. See, for this one the depth is 1 at the starting. Then we go to the second step, the depth will become 2. Then we go to the third, the depth will become 3. Now we just take the maximum depth. This is 3, this is 3. For in even in the right side it will again go check 2, then the right side also give us 3, then again 3, and our depth in the final will become 3. Okay, so sorry, not this one. See, recursion moves data into two direction. Parameter carry the context down from the parent from the child. So return the values carry answer up from the child to parent. Okay, so the every node carries one values, that is simply our depth, and every child pass the depth to the parent. Okay, so the parent goes to the left child and right child, so whichever will be the maximum we just take it. So it passed down one as a parameter shown as blue. Information flowing down the tree always write on parameter like this. Okay, so simply go, the depth will become 2, the actually it is shown in blue. Information like going down, the depth is 3. Now the left child of the depth, left child is null at depth 4. Okay, so if you go to the 4, it is null. An empty subtree has a maximum depth of 3. Okay, because there this is the 3. Okay, so the base case it will return 3, maximum 3, right subtree 3, it return a maximum of 3 comma 3, and it's 3. Okay, similarly every time we are doing it, it is, to be very honest, it is very much simple. Let's go to our today's question, this one. Validate a binary search tree. Okay, so given the root of a binary tree, determine whether it is a valid binary search tree where every node in the left subtree is strictly less than its parent's node and every node in its right subtree is strictly greater. Okay, so actually the context of the binary, so a binary tree, let me clarify, not this one. Okay, so what is a binary tree? A binary tree is a tree which has at most two nodes. Okay, every node has at most two nodes. Only the leaf node, they don't have two nodes. Okay, so if you search like binary tree, so yes, a hierarchical data structure which each node has at most two children. Okay, commonly referred as left child and right child. So similarly, if we search, sorry, if we search about binary search tree, a binary search tree is a node-based binary tree data structure where the nodes are arranged in strictly specific order. Okay. Okay, so every single node in the left subtree of x must have smaller value less than x value. So what does it want to tell? Okay, so this is a binary tree. Now what is a binary search tree? Suppose we have our root as 7. You know for which reason I take 7. This is the left child, this is the right child. Okay, for this left child you can get another child, here you also get left, right, left. So this part, all of this part has multiple nodes. every value should be less than or equal less than 7. See here. Okay, it's not this. So every single node in the left subtree of x must have been value less than x value. So for here, let me bring it to here. Here it is 7. So every value in the left subtree will be smaller, and every value in this right subtree will be greater than 7. So this is the simple condition of a binary search tree. So for any node, the left part will become smaller and the right part will become bigger. That's it. This is a binary search tree. Even it is mentioned here where every node in the left subtree is strictly less than its parent and every node in the right subtree is strictly greater. Okay. So this is the condition of a binary search tree. Simple. So we are given a tree. We have to answer that is it a binary search tree or not. Okay. So I need this one. I need this one. So our brute force approach will become same. I will not write the brute force code, not even submitting on the platform. So we are given a function simply is valid which takes the root. So we have to traverse every node, and for every node we have to check the maximum of the left subtree should be greater than the node. Uh, if maximum of the left subtree is become greater than the node, then simply or minimum of the right subtree is less than equal to node, simply return false. Okay, so what we did, suppose we are given 7 here. Okay, so we have multiple things here like multiple nodes, multiple values. So if any value, suppose anything 8, so 8 is greater than 7, so it is not a valid tree. Okay, similarly for 7, if you go to the right part, there are like multiple things. So if we got 3, which is less than 7, this is not also a binary search tree. So that condition we just proposed here, like if this condition works, then it is perfect, we will return false, and otherwise it will be a binary search tree. Simple. So don't just do this. Let's go down to the optimize approach. So for this, the time complexity will be big O of n and the space complexity will be big O of h. Okay, let's go to our optimize and DFS approach. So we are studying DFS 5381469. Let me draw it. 5 3 8 1 4 1 4. This may be 6 9 6 9. So suppose this is our tree. We have to make sure that it is a binary tree by BST or not, binary search tree or not. It is a binary tree. But how could we tell that? So if we just see it in normally, if I go to the left part, see, try for every node. This is the leaf node, so don't worry about that. For this 3, the left part is smaller, the right part is bigger. So binary search tree. Same for this 8, this 6 is smaller, this 9 is greater. This part is a binary subtree, we can say. For this 5, what is the maximum? This 3, this what is the maximum in the left subtree? 4, which is less than this 5. And for this 5, what is the minimum of this whole right subtree? 6, which is smaller. See, 4, this one. See, this one, we reach the condition. So every element in this left subtree is smaller than this 5. Every element in the right subtree, it is greater than this 5. Even if we take, I just change the color. If we take this small subtree, this small subtree. For this also, this is smaller, this is greater respect to this 8. Even for this subtree, this is smaller, this is greater respect to this 3. So it is a proper binary search tree. Okay, but the question is how we actually go and solve it. So we are using a DFS. So what does DFS do? To be very honest, DFS go to the every node, till the last node, then come back, go to the right part, then come back, then go to the right part, then again left part, again right part, again come back. See, for every node, for this, even this 3, it first go to the left part, then go to the right part, then come back. So whenever it goes to the left and right, if we just check, so we are, suppose, let me take it again here. Suppose for this 3, okay, this is our current node. So we are using DFS. So it first goes to its left. Okay, there is a 1. For this one, we again perform DFS. It goes to the null. So whenever this is a null, or rather, don't take null. Let's take it as a leaf node type of condition. Okay, that this 3 we reach the leaf node here. So this 1 is less than this 3, and this 4 is greater than this 3. So 1 is less than this 3, and the 4 is greater than this 3. So this part actually a binary search tree, a BST. So this 3 will return a true. Okay, similarly for this part, this will also come, this will also come, this will also return a true. And for this 5 checks, is there any false? No. So this 3 is less than this 5. Yes, the 3 is less than this 5, and the 8 is greater than this 5. So it is also returned true. So our last output would become true. So this is how we are using binary search here. Okay, so one condition we could perform here also, that whenever we reach a null, we return true, because null tree is also a BST, because there is nothing. It can be BST. Okay, so we return true here. So this is how we will, not this one. Here we will write the solution. Let me write it. Or can I just show you that? Yes. So see the range for, and you make condition like how for this 3 we just check with 3. So here first we start with minus infinity and plus infinity. Okay, because there is nothing more than this 3. There is nothing more than this 3. So we can simply, and this 5, not 3, this 5, because the 5 is the root, so it should be ultimate, so it should be anything. So we use minus infinity to plus infinity. Then go to the left child, must stay below 5. So high bound is tightness to 5. Okay, so the recurs to the 3 is minus infinity plus 5. So whenever we go to the 3, so we go to the left part. See, we go to the left part, and the left part is always become smaller. So the left part is always become smaller to its parent. It simply means 5 should be the greatest element between all of the left part. So the maximum range become 5. Okay, and the minimum is also minus infinity. Then again is goes to the left. For this left also, okay, for this left also, see clearly here, it also goes minus infinity and 3, because this 1 should be less than this 3. Okay, and this for this one is a leaf node, so it will return a true. Similarly, when you go to the right, okay, the minimum should become 3. See, because we need a value which is greater than 3 but lesser than this 5. So see, we are changing with high and low. So if how could we there may be the question like how we maintain this range. So if we use two values, like two values, one is low, another one is high, simple, low and high, so that help us to maintain this range, like this 3 and 5. See, the range is at 3 and 5. We start with the value with minus infinity and plus infinity, but then we just move it to according to the condition. Okay, so it is true, it goes to the left. So if both of them are true, it should become true. Okay, now it goes to the right, so right. See, it goes left subtree is valid, go right. Our right child must exceed 5. So every value should be greater than this 5. So the lower bound will become to 5. The lower value will become to 5 and the upper will be maximum to anything. Similarly here, see, the lower bound is 5. A lower value is 5. The maximum value is infinity, and 8 is this value, this node value. Okay, then go to the left child. For this left, we have to make sure that no value increase this 8, so the range will become 5 6 8. Okay, it return true. Then it goes to the left, it will become greater than 8, so 9 is greater than 8, it will return 2, and again this will return 2, and at the end this 5 will return 2. So how did we have this, do this using DFS? So we are taking a valid, it is simply a function. Take the node, take the node, take the low and the high. Okay, so if the node is equal to null, simply return true, because if it is null, it can be BST. So if check the condition where the in which condition it is violated. If low is less than node value is less than high. So this is our condition to make sure that the value is perfect. So we are using a not here. If we don't reach if any node don't follow this condition, like this low is lesser than the value and the high is greater than the value, simply do return false. Okay, now simply do one thing, valid of, go to the left part, so node left, our see, whenever we are going to here, come back. So see, for this 5 8 infinity, so whenever we go to the left, does our low value change? Our low value change? No, the low is same, but the high is changed to this node value. So when we call this function valid, we go to the left part, our low value will be same, our high value will be node value. Okay, and again we have to go to the right part, so node right. So what happen when we go to the right part? See, this one, so this is minus infinity 3 5. So when we go to the right part, we have to make sure our minimum will become 3. See, our high became same, both of the cases it is 5, but our minimum it will be from minus infinity to 3, it will become. So our low will become node value and our high will become the high. Simple. Oh, this is the code. There is nothing more than this. Yes. So Oh, today is YOLO. Nice, by the way. So this is our code. Now let me write down the code. So this function doesn't contain anything as low and high. So it's simply make we will make another function which is also is valid BST. So let's take it solve. And what does it takes? Where it is goes? This one. So it takes a node. Let me change the color. It take a node, a low and a high. Low and high are integer variables. So it take the node. Take is a root. It take the low and the high. So okay. Now if the node is null, return true. Okay, so just change the variable name from node to root. If root is equal to null or not equal to root, you can do it. So return true. Go to a second condition. If it not valid this condition, low less than node. So if the node value, the root value is less than equal to low. See here simply low is less than let's take it value, but when we are checking that the opposite condition we take, that if this will happen, then we simply cross it. So anytime our low value will become greater than our value and root value is less than the node value, it will become greater than equal to the high. Simply return false. Okay, so what happens, see here, our low value is greater than our node value. So our low value is greater than our node value. Simply we have to make sure our node value is less than our high. So we just check if our node value is greater than our high, so we return false. I just opposite it, I just opposite it. And then what we did, we go to our left part and right part. So simply return solve root. For this left part, we need our low to be same, our our high to be changed with node value. So it will become node left low and root value. And now go to the right part. So root right, then we change our low to node value and high will be remain same. Then we change our row to node value, which is nothing but root value, and then simply our high will become same. This is the, but remember, when we start it, we start with minus infinity and plus infinity. So we have to make sure we return here the solve function with the root. A low will be int minimum and our high will be int maximum. So this is inbuilt value in C++. It is minus infinity, it is plus infinity. Okay, let's just run it and check it, is it working or not. Okay, it gives us a wrong answer. We are doing it right or not? What we are missing? The root value should be less than equal to low, the root value should be greater than equal to high. Then you simply return false, otherwise go to the left part. When you go to the left part, the low and the root value go to the right part. It will become root value and high. Okay, are we missing something? The number of nodes in the trees range from 10 to the power 4. Does it have to do long? Let me check it with this. I think we do an logical mistake somehow. Okay, let me check. The problem is this one, because this should be or, not and. Because because uh, because if we go to the root left part, we should have checked the left, not the whole left and right. And if there is a null, it will also return null. So we need to make sure that this should be or, this should not be and. Okay. Okay, it gives us a wrong answer. Okay, so root value is very much maximum. So use long. I think this should work. L long mean and L long max. Yes, let me submit it again. Yes. So we have to make sure this should become and this should become long, because this one, the node values can be the maximum one. So we need more larger value to put the minus infinity and plus infinity. For that we are using this long max and min. And this should be and. This should be and, because this should not be this should be or, always or, not and. It should be or. I make it as and, but this actually should be or. And this is our question. So you can see the time complexity here also. Our time complexity will become big O of n is the number of node, and our space complexity will become big O of h, and h is our height of the tree, and it is the recursion stack space size. Okay, and this is the big O of n because we traverse every node. So this is our solution to this very simple question but interesting question, valid binary search tree. This was the question. Go check this question, use this platform, use this link to get a 7-day free trial. Use this platform at dsa.chaicode.com. Thank you very much.